Hello and welcome to our Tips and Techniques videos. I'm Mark Biasotti and we are currently in our advanced modeling episodes. And over the next 30 minutes or so, we'll be exploring how you can increase your skills using some of SolidWorks' more advanced features so that you can be more productive and create higher quality models. So whether you're a seasoned SolidWorks user or a beginner, we think that you'll learn something new in this series. For your convenience, we've listed the topics in the YouTube description that we'll be covering in today's episode, along with a timestamp for each topic in the video. Feel free to skip ahead to any tip or point you want to learn more about. This series is being brought to you by Spanner Product Development, a product development company dedicated to creating positive impact in the world, merging innovation, sustainability, and responsibility to bring meaningful experiences to life for over hundreds of clients. If you want to learn more about what Spanner has to offer, stop by our website at spannerpd.com or email us at hello@spannerpd.com. Now let's get started with this episode of our Advanced Modeling episodes. Welcome to our Advanced Tips and Techniques series of videos. This is episode 8, and this is Introduction to Advanced Modeling Features. And today we're going to take a look in more depth at the advanced modeling features that you can use in SolidWorks. These are, of course, the features that go beyond just extrude, revolve, and fillet. We're going to talk a little bit about what is when is the best time to use solid versus surface features, and then what features are best for what types of shapes that you need to create. So an overview of some of the features we're going to discuss are represented in this slide, and again, they are not exhaustive of all the types of advanced features you can use in SolidWorks, but they are a good representation of what you have available to you. And I'd just like to spend a few minutes to review them and give a general description of what they are and what they do. So, of course, in SolidWorks, anything that pretty much that you can extrude or revolve in a solid, you can also do as a surface. So we need to include that into what we can do when we do advanced modeling. In addition, you can create planar faces, which are exclusively just a surface feature. So any profile that is planar can be made a planar surface. And then the three powerhouses, if you will, are boundary, sweep, and fill. I'm not going to talk much about loft here because loft, for a lot of intensive purposes, is a legacy feature, and boundary has replaced it in almost every aspect. I'll talk a little bit more about that. Moving on from that, you have sweep, which basically is taking any 2D profile or even 3D and sweeping it along a path. And again, I'll get into some of these more basic and important advanced modeling features a little bit later. Fill is a unique feature that can fill an area like boundary can, but it can do it regardless of how many sides you have or how many boundaries you have to fill in that area. Some of the other advanced modeling features that can be applied that don't rely on reference or sketch geometry or curves. Dome is a powerful one where you can take an existing face and you can convex or concave dome it. Fillets that go beyond just arc fillets into C2 or continuous fillets as well as conical fillets and elliptical fillets can be considered advanced modeling. Freeform is a feature that where you can take an existing face and start to push and pull on it. Think of a handle grip would be a good example of that. And then there are some other features in SolidWorks that are useful from time to time. Deform is where you can take an existing face or faces and deform them with a sketch or another solid body. Flex is a powerful one in that it gives design intent. For instance, if you're designing a flex circuit and you want to have it in its flattened state and its flexed state, that is having a bend in it, flex is a good feature to do that. But it can also do advanced modeling as a feature in your advanced shape. Rule is a non-sketch based feature that works on existing model edges or surface edges to be able to rule a surface along that edge in a number of different ways, either normal or tangent to it, but also by a vector or by a vector with an angle, and is very useful for creating reference surfaces as you use those reference surfaces to build your main surfaces. Now, I mentioned a little bit about Loft being a legacy feature. The boundary surface was introduced, I believe it was introduced about 2012. I could be wrong about that. No, I'm wrong about that. I think the boundary surface was introduced in 2007 actually, even though it was worked on for a few years prior to that. But in 2007 it started to take over some of the functions that Loft had been doing for quite a while, but then added some important new aspects, and that is basically quality. The ability to maintain tangency on both the first and second directions. Loft was more of a sweep feature actually underneath. It was taking a number of loft sections and then calculating a path using the guide curves. This is no longer the case with boundary, because boundary will give equal influence to all four sides or all two sides. And I'll get a little bit more into when you want to use boundary versus some of the other advanced features. But as you can see from the list here, boundary will do most of what Loft can do. There's a few exceptions left still. Loft can do a center line loft, meaning that you can create a number of loft profiles and then one path between those loft profiles to get a general solution. Loft, you can also insert a loft section into an existing loft feature. There's a pretty easy workaround with this for boundary in that you can just roll into the boundary surface and then create another sketch and then include it. Loft's insert loft section was a little bit more automatic in doing that. But as you move down the list, you see that Loft starts to become deficient in some important areas, and that would be having equal curvature on all four boundaries of the loft section. It also cannot create connectors in both directions. Connectors are really important with the flow, or what you want to determine to be the flow of your boundary. We'll talk more about that in a future episode when I'll dedicate the entire episode to boundary. And then boundary is higher quality than loft. One of the areas that this is true is that if you were to create a loft with guide curves, the guide curve is just an approximation, because remember I mentioned that underneath the covers, so to say, with Loft. It's doing loft sections and then basically sweeping those. Well, when that happens, the guide curves are close approximations, but they're not completely accurate. Boundary is just a different algorithm. It doesn't work that way. It, again, as I said before, it has equal influence on all four sides of the boundary. And another very useful feature about boundary is that you can create a boundary with only a first and second direction curve. Think of a cross or two curves that cross each other. If you assign the first part of the cross as first direction, the second part as the second direction, then you get a general solution between the two. And I find that really helpful. So the natural question would be, for people who are unfamiliar with advanced modeling and the advanced modeling features of SolidWorks, is I have a lot of these features that you're offering me. How do I use them and when do I use them? One of the first questions to ask is if you do need to use it to create an advanced shape. And in some cases, the answer is no, you don't need to use an advanced feature to do that, or you don't need to do it. You don't need to create it as a surface, but you can create it as a solid. Now, many of these advanced modeling features, like loft, boundary, fill, sweep, can be executed as solid features. They don't need to be a surface feature. But I think what you'll find with surface models or advanced models is that they need to be broken down into patches of design intent that you build separately and then knit back together to make your final form. And I'll talk a little bit more about that very soon here. Some other things that I think are just general good guidelines is that if you're not sandboxing or doing just exploratory, but you're actually implementing a detailed design solution in SolidWorks, I would avoid doing exotic solutions. Try to find the simplest and most robust way to achieve the shape. And even though it might be tempting to use something that's a little more exotic or esoteric, if you're mindful of others, especially others that are working with you that may need to go in and do modification to your design, trying to keep it simple and direct is really going to help them. So keeping these in mind, I think, really helps to build more robust models, but more understandable models. And it would cut down on the number of features also, which is another important decision or a result of the decision to make whether it's solid or surface. So let's just use this bottle shape as an example. You can see that on shapes like these, there really is no direct way to build these as solid models. Sure, you could start with a solid rectangular form and start to cut away at it. But as you cut away at it, you've got to be very careful that as you cut away, you're maintaining a tangency or even curve continuity with other design elements. So traditionally, the best way to deal with this is to build it from surfaces up into a solid. And I can bring this model up and review a little bit with you on how that's done. But you can see that this model itself employs a number of the features I just mentioned. A lot of boundary surfaces, a few fills, and even some sweeps. And what you don't see in this model is that it's actually symmetrical. So you're seeing the front half of the bottle, and as these are built up, it's mirrored to the back half. So, like I say, most consumer products have some symmetry in them, and bottles like this usually do. But from this front view, it's not symmetrical, and so there's a lot of individual work, a lot of individual design intent that needs to be built up to achieve the final form. So what surfaces are best suited for what shapes? And this is a generalized slide of 3 of the most used advanced features: boundary, sweep, and fill. Boundary is a feature that is necessary when you want to make an algorithmic surface between 2 or 4 boundaries. When I say algorithmic, I mean it's an advanced swoopy shape. It's not analytical, and it's usually created by creating a network of curves to define its boundaries or existing edges of a model that are not linear. And it can do tangent matching as well as curve continuous matching. So it's adequate for a lot of consumer product design. Sweep is a feature where the nature of your design intent is a shape that generally holds the same cross section but changes or goes through a path that changes. And I say generally carries the cross section. A simple sweep would be a profile and a line, which would make an extrude. If the line were curved or a spline, it would be that profile sweeping through that nonlinear path. By adding more paths, or what we call guide curves, you can constrain the profile to change as it goes along the path, and that makes for a very powerful feature. I also believe that sweep is probably the highest quality surface you can get, because the surface itself, as the profile sweeps through the path, it's conical cross sections that never they're just higher quality because it avoids inflections, and you just get a much nicer result if you do things right. And it's very powerful also because it's defined by so few elements, that is a path and a profile along with maybe a guide curve. Fill is an important feature when boundary cannot satisfy the requirements. So boundary only really works between 2 or 4 boundaries, and those boundaries have to be fairly perpendicular to each other. With fill, it's quite a different story. So there are advanced shapes where the requirement calls for something other than a rectilinear patch. It might be 5-sided, it might be hexagonal, it might be a triangle. And so that's why I describe fill as a shape that is really suited for 3 or 5 or more boundaries. And it works very well because it doesn't derive, and this is to assume that if you were to create a fill or a boundary, that you want to derive tangency at the edges that you're filling. Fill has a unique algorithm in that it has a generalized tangency or curve continuous matching that doesn't rely on those boundaries. And so you don't get problems at the corner like you would on boundary. And again, I'll go into more depth about all of this when we cover these features in a future episode where we can really start to look at this in SolidWorks, and I can explain it much better. So I have a few example models to bring up, and the first one that I would like to bring up has to do with when it's best suited to use solid modeling or stay as a solid model than use surfacing. So if we take this as a simple example, let's say, for instance, this is a switch cap, and you've got a lot of them to create. And maybe they all vary in length or the height of their dome. This particular example, I run across this example in industrial design a lot. And as you look at it initially, you would think, well, I really need to do a surface model to get the top faces of this dome. So it's logical for this model to extrude a profile and extrude it with draft, if it's a molded part, which it probably will be. But from this point on, I mean, how do you get that dome in a very robust and simple way? Now, you might want to use the dome feature, but unfortunately for shapes like this, dome doesn't work that well. Let's try that. So if we were to pick this face and apply a dome feature to it, we get a preview, and dome's an excellent feature because it just is created by picking a face and then giving a height of the dome. And let's say that we want, just for the purposes of this, we'll make it quite a high dome, maybe something like 6. I'll just leave it like at 10, just so that we can see what's happening here. And then go ahead and complete it. Well, it does produce a nice dome feature, but it has an aspect about it that isn't quite right, and that is it assumes that all the boundaries start normal to the edge of the boundary. And so we're going to get a shape that isn't quite domed. It's somewhat of a derivative of a dome. And that might be the design intent. And if it is, by all means, use this. I'm finding that a lot of times this is not what the designer had in mind. So we have to do something other than use dome. So what we can do is, if we're talking about a pill shape that is capped at either end, I think the best way to handle this would be to basically try to stay in solid as much as possible. I try to avoid taking solid models and then deleting one of their faces to become a surface model. You do that by selecting on the delete option of delete face. And now we have an open surface body that we can create some surface modeling to cap the top of this and make it solid again. That's not necessary that you have to do that. And I'll show you what I do, or as an example, to keep it as a solid. So let's just keep using solid modeling as long and as far as we can. So I'm going to, again, just do an intersection curve on this face. I'm going to draw in an arc that represents my dome. And we'll just make that something like 50. And then we'll take that profile and we will extrude it up the vertices where these start to curve, and do it in a second direction. You know, of course I could have just put a plane here, a plane by the right at a vertice, but then that's an extra feature by 2. So I'm really trying to keep my feature count minimum and do the most intuitive thing you can do, and that is to stay in solid. So now I have part of my dome. Now what do I do about the end caps? Again, I could delete surfaces here and maybe do a fill, because remember, this is really 3-sided, because you do see just 2 boundaries here, but these coming to a point and these boundaries sharing the same endpoint is also an issue, and I'll get into that in more detail in a future episode, why you wouldn't want to do that with boundary. You could do it with fill, but the simpler thing to do is then just pick this face, do a convert edge. Let's take this, well, let's just delete this sketch element. And then simply, because we have a center point here for this, we're going to draw a construction line. And then we're just going to simply revolve that I said revolve, Mark, not extrude. And just give it something like 15 degrees. And now what we have is something that we can use to finish off this solid and make it more like a complete dome. And with that surface revolve just completed, I can go to replace face, pick this bottom face and replace it. And there I have my solution. I can roll before that, and probably I would take that surface body, want to select it here, and mirror it across this plane right here. And then as I have one for each of my caps, I can replace that, and then I can also replace this one. Oops. Need to pick this as my surface and replace that. So that's what I mean by looking at a design problem and finding a solution that is as simple as possible. And I know that this isn't possible in many situations, but a little bit of thought given to how you would approach a problem like this might render an easier solution if you're able to think about it a while, and especially think about how can I stay in solid instead of going into surfacing. So I talked a little bit about different surface types, and this model of this tire pressure gauge is, I think, a good example because it really employs quite a few different surface types or advanced modeling types. If you roll back on this model, and I'll supply all these models that you can download, you can look at them for yourself. There's some important features in here that highlight what I've been talking about, especially when it comes to sweep and boundary and fill. And in fact, what you're seeing here is a swept surface, a fill surface, and then if we roll forward a bit, that's a boundary surface, and then a fill surface. Let's look at each of those. If we roll back to the handle, I chose a sweep here just because of the quality that I wanted to maintain through this part of the pressure gauge, especially this is where your hand engages it. And aesthetics, but not only aesthetics, but feel are really important here. So that's why I wanted to try to achieve a really nice solution here. The way this was done was, if we take a look at the feature itself, well, of course we have a profile here, and this profile is probably a conic. And if we actually show some of the curves that are used for this, it might make a little more sense. So before I roll into that or edit it, let's turn these on. So what we have going on here is we have a profile, which is represented by a spline or a conic. We have an actual path here, which is where that conic starts and sweeps all the way to the endpoint. And then we have two different guide curves. And what's powerful about this is that the profile itself is constrained to these guide curves with a pierce. And as the profile moves down its path, and we can start to evaluate that a little bit better if we use this little feature here. Well, maybe not. Yeah, there it is. So you can see how it's moving down the path, but it's maintaining its beginning and end points along the guide curves. And what's especially powerful about SolidWorks Sweep is that as you do that, it can solve the solution all the way down to the endpoints of where the two guide curves and the profile or the path meets. And that's really powerful. And so that's what's happening there with the little yellow preview. And if you look at this with some curvature display, you'll see that it does a very nice job of generalizing that surface through the sweep. You get a little bit of degeneracy down here in the corner, but it's not bad enough to make it fail as a shell or offset surface. So that is an example of how you can use sweep in an advanced modeling situation. So let's just hide a few of these and move on. We'd have to roll further in the model to this feature. Now this feature is a boundary surface that is bounded by 5 curves, or 6 curves actually. So in my first direction, I have this curve, and then as I go towards the stem, I go to my second first direction curve, and then down to my third. And then if we look at our second direction, we basically have the profile at the parting line, and then an interim here, and then the other, I'm sorry, this is the other, I'm getting confused here. This is the other profile at the parting line. And they're both normal, and then that's the interim curve. And then on top of all that, we have, we also, in this model, or maybe another modified one, I've put in some connectors which further define the flow of the actual resultant surface. But again, we'll get into more of that when we start to talk more in depth about boundary. So that's your boundary. We roll forward to our swept handle. And then what we're left with is, and this is often the case with advanced shapes, is something that is not a boundary or a sweep, but it has multiple sides. And this is where fill is a good solution for figuring out how we're going to finish off this model. So I put in a number of reference surfaces and other geometry, and you can see I've laid down some curves here. Those are to define some interim curves for the actual fill. And then as we go forward, I actually have another little boundary surface here that's just for reference as we continue to go for our final solution. And there's some more boundary references here, and these are important to hold the edge tangency or curvature for the fill. Fill works best when it knows that all of its surrounding boundaries have some kind of direction in that adjacent surface. And so those are reference. And then a couple split lines to make it more exacting for the fill surface to understand what to fill. And then even more boundaries for reference. And then the final well, almost the final. I cap the end here, and then we go into our main fill surface here. And you can see with this fill, we're not only using all these surrounding boundaries, of which there is 1, 2, 3, 4, 5, 6 of them, but we're also using some interim curves to further define the shape as it fills in between those boundaries. It's not likely that you'll be able to use more than 2 curves here. Even using 2 curves here is rare. Usually fill works best with either one interim curve or a constraint curve or a point. Using 2 or more is probably not going to result in something that you would expect. So again, we'll get into fill and probably dedicate an entire episode to fill so that you can see how you can use that powerful feature in a really great way. So that's representative of 3 of those main types of advanced modeling features. I promised you that we would take a look at the Downy bottle. The Downy bottle is more complicated than the last example, as you can see through the slide, the PowerPoint slide. We have some reference here, and then if we go into our main surfaces folder here, you can see that this Downy bottle has quite a few features. Let's see, we have about 180 total features for this. And if we were to turn on or turn off our hide edge tangency, we'd be able to see that. So let's do that. So you can see it's made up of a patchwork of different surface types so that the overall form looks very continuous. And it's really the only way that I know how to do this. Actually, the better way to do this, but as a SolidWorks standard or pro or premium user, you're not able to. You can do it with some add-on products, is to do a subdivisional surface model. Subdivisional surface models are really good at this kind of shape because it's a completely different paradigm of starting off with primitives and then pulling shapes or pulling nodes on that subdivisional surface to divide it and to work from a soft morphic form into more definitive form. Again, if you just do a Google search on SDS or subdivisional surfaces or NPower's power surfacing, you can see how that works. And if I had the choice, I would probably do it as a subdivisional surface. But if you don't have that capability, or your client doesn't have that capability, and you need to pass this model on to them as a native SolidWorks model, then it's really your approach is to build up a number of surfaces into a patchwork and then becomes a solid. So with that, I think I'm going to conclude this episode, and we can move into more detail about these various features and how you can use them, what are their options, and how they work together to come together to make a final solid form.
Thanks for tuning in to today's episode. We hope what you've learned has been informative and can help you to better use some of SolidWorks' advanced features. You'll see in the YouTube description a link to example models used in today's video. Feel free to download it, and you can explore these techniques at your own leisure. Also, we'd love to hear from you, so consider emailing me at the address you see here on the screen. If you need help on your design project or just want to know more about us, stop by our website at spannerpd.com or email us at hello@spannerpd.com. Take care, and I'll see you in the next episode.